Okay, so this is the coin toss simulation presentation. It's presented in PowerPoint. The coin toss simulation was done in Python, and my name is Christopher Kevin Prinz, presenting for Clark Wellman's Section 4 Computer Science 110, spring quarter at Seattle Central Community College. So first off, a little bit about the theory of probability and how it relates to coin tossing. So if I toss a coin n times, the probability that it's going to be heads is pH, and the probability that it's going to be tails is pt. And pH and pt will add up to 1. We're assuming that the coin is never going to land on its side. It's going to be one or the other. So then the probability of getting m heads is determined by the equation n factorial over m factorial times n minus m factorial times the probability heads to the m and times the probability tails to the n minus m. So to give an example, if you flipped a coin 5 times and the probability of getting heads was to predict the probability of getting 4 heads, it would be 5 factorial over 4 factorial times 1 factorial times 0.5, we're assuming it's a fair coin, to the 4 times 0.5 to the 1. And that would give us the probability of getting 4 heads out of 5 coin flips. So this equation is actually going to lead us into our codes and functions. So the predicted results needed to be determined so that we can compare them to the simulated results. And the first 3 functions of the simulation do the predicted results. The first determines the factorial part of the equation. The second determines the numerator and denominator of the n factorial over m factorial times n minus m factorial. And then the third part puts those two together with the probability of getting heads to the number of heads and times the probability of getting tails to the number of tails, and then returns the value. So the third function calls on the second one, and which in turn calls on the first one, to give us this nicely written 3 functions that return the predicted results for any given toss. Our next function gets into the actual flipping simulation. So it uses the random module, and determined by the number of times you flip the coin, which is set by the parameter times, and the probability set by the parameter prob of it coming up heads. We're only calculating heads right now. So this is the first part of it is a counter that's set to 0, so it's an initialized sum accumulator. And then it runs a for loop, and then it assigns flip as the random, and it runs through the amount of times, and if the flip comes up as being less than or equal to the probability, which let's say it's 0.5, if it's less than 0.5, it'll give it a head. If it's greater than 0.5, it won't add the head to the counter. All right, these are 2 functions, and the first function I've dropped out the formatting statement so we can just look at the meat of the functions, and in the second function it calls upon is us running the set of numbers that we want to do for our simulation, and it calls upon the toss function to do that. So let's talk about the toss. The toss opens a file, and the file name could be anything. You could do a new file and have it be .text, whatever you wanted it to write in, and then the A appends it. And then it initializes a dictionary, sets up a couple of sum accumulators, and then it runs through a few for loops. The first for loop sets the keys at 0, so that even if a result didn't return, you would still get a 0 in your simulated results. And then the second for loop assigns a value from the flip. So it's going to tell you each time you went through the number of tosses, it's going to tell you how many times you ended up with heads in that toss. So let's say it was 3, then it would add 1 to the 3 key. And then for I, in key, is going to it's going to change the value. It's going to change the value for the I key to be the percentage out of the number of sets that we did. So it's going to give you the simulated results for each amount of heads. And then the second for loop assigns a bunch of values that we're going to need for our table, and it's the predicted values for each set of flips. It's the error between the simulation and the predicted, and then the relative percent error between the two, and then the last two parts are just adding to the sum accumulator so that we can make sure that our probability heads and probability tails is always adding up to 1. And then the main is a bunch of for loops, two of them nested inside the other one. So for each for loop, there's 4 different variables. So it's going to be 4 times 4 times 4, which is going to give us 48, which is why we end up with 48 tables in our printout. And then it runs through TOS, N, M, prob, and it does each set alternatingly until it gets every combination through. So let's actually look at the code. And now for something completely different, because we're in Python, and I thought it'd be funny because we're in it was named after Monty Python, but actually it's not completely different. We're just going to switch over to Python to look at the file output and the coin toss simulation. All right, let's start out here by looking at the code, and we'll go over this kind of from the top. So we're going to import the random function, from the random module, and this is going to be used later in the flip function. The first one is a factorial, parameters n, sum accumulator, or product accumulator. For I in range 1 to n plus 1, it's going to accumulate the factorial. So if it was 5, it's going to be 5 times 4 times 3 times 2 times 1. And then it's going to return that accumulator. For C and M, parameters n and m, it's going to it's going to assign the numerator as factorial of n, the denominator part 1 as factorial of m, and the denominator 2 as factorial of n minus m. And then the denominator is going to be denominator 1 times denominator 2, and then it's going to return that. And that'll be useful for predicting the probability of heads here. And we're going to get the probability of tails from minusing the probability of heads. We're going to get the number of tosses for the number of tails by taking the number of tosses minus the number of heads, and that'll give us the number of tails, so that when we plug in the first part of our probability equation from this, then we can easily plug in the second parts, which is the probability heads to the number of heads and the probability of tails to the number of tails you end up with. The flipping is a super simple function. It takes times the number of flips you want to do and the probability. And let's say it's a fair coin, so we'll say the number of times is 5 and the probability is 0.5. So for I in range of 5, every time it flips it, it's going to compare it with this if statement to the random function. The random function picks a number between 0 and 1 randomly, and then if that number is less than 0.5, it's going to add to the head counter. To talk a little bit about the toss, the toss first opens an out file, assigns out file as the opening of cointossproject.txt, and it's appending to it. It's appending to it instead of writing to it, because if you write to it, it erases the results every time you run through the program. So I didn't want it to do that. I just wanted to add to it so we get all of our 48 tables. Set an empty dictionary, 2 sum accumulators to do the probability, the sum of the probability of the simulation and the sum of the probability of the predicted. And then it's going to run these 3 for loops. The first one sets up the keys and initializes them at 0. The second one actually runs them through the flip m times. And then inside the second for loop there's an if statement. So if h has already happened once, it just adds 1 to that key. And since h has happened once, because we already set up the keys, it's just going to add 1 to the keys we've already set up. And then the third for loop takes for each key and it gives back the probability, the simulated probability out of M. Then we have some formatting statements. Let's open this up a little bit. We have some formatting statements to that are just going to help set up our table. And then we run the main for loop. The main for loop here gives us our predicted results, the error, the relative percent error, and adds to our accumulators so that the sum of the probabilities will equal 1 in the end, hopefully. This last print statement is going to actually print the results to our file for each of our headings. So I will be the number of heads, and minus I will be the number of tails. The simulated probability will be key I, remember being assigned by the for loop here. The predicted results will be the predicted prob, and then the error between the simulated probability and the predicted probability, and then the relative percent error. And then the file out here at the end of all of these files it to the CoinToss project.txt. The last print statement here, other than this other one, which is just a space, actually is going to format our sums for the simulation probabilities and the predicted probabilities. And then our main loop here is going to run through each of these variables, and it's going to line them up with each of the other variables so that we run through each of these. So we're going to run through 5 times 1,000 for a probability of 5 times 5,000 for a probability of, and then so on and so forth. So let's actually look at our results. So from our results, we find out for the first set, number of tosses 5, and we did it 5,000 times. The number of times that it comes up heads is given here. The number of times that it comes with 0 heads is given here. The number of times it comes up with 1 head each time, it's here. 3 heads, 4 heads, 5 heads, and then the sum is 1. And then for the predicted probability, we can see the difference in what happened in the simulation versus the predicted. Although the results are very similar, they're not the same. So then the error gives us the difference between that. So actually, like, what was different between the predicted probability and the simulated. And then the percent error gives you an idea of like how much it was off by. And then you can see for each result, it gives a table. All right, and then without knowing the probability of getting heads, we can look at these results and kind of determine that the coin wasn't fair or was fair based on the patterns we see in the results. So we can compare directly here the probability of getting heads being to 0.6 and the probability of getting heads to 0.5. And you see this pattern like where it's heavy numbers on the top and the bottom, and then they sort of get close, but they get close here, and then on the simulated results they should sort of match up on the 2 and the 3 for the 5, but they don't. They sort of like gear more towards getting more heads. So you can just see the number of heads coming up is happening more when the probability of getting heads is greater than the probability of getting tails. So that's my code, Professor. Thank you for everything. The project was great. I finally figured out how to fix the sum part of this. So have a great summer.